Okay. Good afternoon, everyone. It's a Friday afternoon, so it's my great pleasure to introduce my PhD supervisor, my mentor, Dr. Satish Ukkusuri from Bard University. So Dr. Ukkusuri is a Riley professor in the Lice School of Civil Engineering at Bard University and director of Urban Mobility Networks and Intelligence Lab. His research is in the area of interdisciplinary transportation networks with current interest in data-driven mobility solutions, disaster management, interdependent networks, connected and autonomous traffic systems, and smart logistics. He has achieved numerous awards, and he has published more than 350 peer-reviewed articles, and he's currently the editor-in-chief of Journal of Big Data Analytics and the chief of ACM Journal of Autonomous Transportation. So without further ado, I'll let Satish speak.
Thank you, Samuel. Good afternoon, everyone. It's a great pleasure to be here. So this is a Friday afternoon, so I'm going to kind of keep this to a short presentation. There'll be some mathematical equations, but we'll try to keep them as easy as possible. And so it's a great pleasure to be here at UCF. This is my, I think, third visit to UCF. Every time I come here, I get more and more attached to Orlando. So this time I actually also brought my family here because I really wanted to show them all Orlando has to offer. And so this presentation today, when Samuel contacted me about this Smart City initiative, he wanted to do something related to smart mobility, and we do a lot of work in that. So I presented during my previous visits some of this work. So today I want to kind of talk about some of the things related to energy optimal transportation systems, particularly from a DOE project that we have worked on over the last 3 years, coming up with efficient ways of integrating operational tools into a simulation model for evaluating various types of smart energy transportation solutions. So this work is done jointly with some other collaborators, including my PhD students. So they did most of the work, but today I get here to stand in front of you and make this presentation. So if you look at transportation, one of the biggest consumers of energy, so we all know that. So it's about 28% of energy consumption in transportation. So how can we even make a small dent in terms of reducing this energy consumption, coming up with efficient mobility solutions using AEVs, autonomous electric vehicles, as solutions, but by focusing on some of the largest energy consumers in transportation systems, which are the transportation hubs that are there in urban areas, rather than really looking at the entire network. If we were to just focus on transportation hubs and reduce the energy consumption in them, can we really see some effects of this? So that's the supply side kind of measures. And on the operational side, can we come up with novel ways of routing, of matching these type of vehicles, and creating scalable tools to reduce this type of energy consumption? So this is the overall focus of this METSA project, which is multimodal energy transportation simulation in real time. And this is my overall framework. So I want to kind of first talk about some of the energy inefficiency that is actually there by using data to kind of show you some of these things. And then I want to go into the operational algorithms related to echo routing. Then looking at online ride sharing algorithms. And then looking at the bus adaptive schedule kind of a problem, which has multiple applications in urban areas. I also want to kind of share with you some simulation related tools that we actually have developed as part of this study. And then finally talk about some ongoing work on human-centered charging infrastructure type of ideas for using large-scale location data for looking at charging corridors. So a lot of things to cover here. So I'll try to kind of keep it short, just kind of give you the main message of each of these different types of methods. And if you have questions, we can kind of go into more details. So do we have a pointer? Let me see if I can use this. Okay, I think this may work.
Yeah.
So this MetSearch system consists of three parts. The first is a data part, which includes different kinds of data that we are actually using and collecting as part of this. It includes taxi data, it includes map-related data, different types of location data, and so on. The second is some kind of an analytical platform, including operational tools, which includes demand forecasting, ride sharing, routing, and doing trip analysis based upon this, and looking at various kinds of operational algorithms related to ride sharing, pickup location, reducing empty trips on the planning side of things. And then finally, we have a simulation module, which relates to looking at developing a HPC platform, a high-performance computing platform, which integrates the data, matching up all of this data, and then these operational tools within this type of a dynamic routing and AUV rescheduling kind of a problem, right? And then coming up with efficient ways to simulate these different scenarios, and finally doing the validation and evaluation of this for different types of energy scenarios, right? So this is the overall architecture of this type of a framework that we actually have here. And I want to touch upon each of these a little bit to give you a flavor of what we have done, what type of results we actually have towards the end when we evaluate this on various networks. So part one, I want to first talk about, before even going into the MetSearch, some interesting work we have done 4 or 5 years back in terms of using Uber type of data to understand the inefficiencies and why we really need to focus on hubs, why we really need to focus on reducing this energy consumption, right, when we have this emerging type of transportation services. And I'm going to kind of give you Uber as an example, but you can kind of put any other FHV as part of this. It could be Lyft, it could be Via, or any other types of ride-sharing service. So the basic question that we have asked here is, while the mission of many of these ride-sharing services like Uber has been to make things better in cities, be it in terms of sustainability, be it in terms of access, do they really do that, right? And if you look closely, the answer is more mixed than what most of you see in the media. And this is the type of analysis which we were really interested in doing when we started off with this project. So these are the different types of data sources. So you can kind of see it has different types of taxi data, GIS data, open data related to ACS. Then we have also FHV data from Uber and Lyft. I'll talk a little bit about how we did this data collection. Although we have an NDA with Uber, we are not able to get the trajectory level data from Uber because it does not share with anyone. And we have other types of data related to other modal movements as well as weather and airport-related data, right? So this is the mission of Uber. If anyone looks at the business plan of Uber, this is the mission is what you can see that, read that, right? So it is to make smarter transportation with fewer cars and greater access, right? But if you see the actual things that are happening in cities, and let's take New York City as the example, right? So if you take New York City, the number of TNCs, the Transportation Network Company vehicles, have expanded rapidly in recent years. So from 2012 to about 2017, the number of FHVs have more than doubled in the New York City, adding to a lot of extra miles that are traveled, right? The VMT has increased in these cities and leading to new concerns related to urban traffic management. So remember, this is the goal. This is the goal of these FHVs when they actually start off with. And the question is, do they really make things better in cities in terms of sustainability? Do they really reduce fuel consumption, right? Do they really reduce emissions, right? And so, right? Those are the things which we would like to kind of test. And this is a very hard kind of analysis to do, because anytime you do an analysis and put out there, Uber can always say, well, but this is not because of FHVs, it's because of a lot of other effects that are there, right? So it's a very difficult thing. So you need to do it in a very controlled setting, this experiment. And what we have done is we have created this type of a control setting to gain accurate insights into the effect of these transportation network companies, and we have kind of used various types of data to make sure that there are no additional effects that are entering into this particular problem. For example, here you can see that the population, and there are two time points which we are going to take to do this comparison. One is 2017, the other is 2019, right? And the population is almost the same, so you can't blame the effects on population changes. Employment is more or less the same, right? The number of vehicle registrations are exactly the same. Whereas if you see the number of TNC drivers has increased by more than 50%. The number of TNC trips have almost doubled, right? And the number of daily taxi trips have actually dwindled, right? Have actually decreased over this time period, right? And we have also checked with NYC DOT that there are no major transportation projects that were actually happened during that time period, and so that there are no other confounding effects which come into play during this, right? So since we do not have trajectory data, what we did was we actually collected this data using the API by ourselves, right? So we actually used a methodology which we can discuss if someone is interested in more detail, or you can look at our paper. Using the API and the ping client message, we actually corrected the various trajectories by installing 470 virtual stations in New York City, and we collected this trajectory data for all of the trips that are there from April 7 to May 3rd, and then from February 7 to March 13, right, for all the different kinds of Uber trips. What does this data contain? It contains the type of service it is, whether it's a Uber X, Uber Eats, and so on, the type of service that is there, the driver ID, and the lat and the long, and so information about the bearing and so on, right? So it kind of gives us the trajectory information of this particular different types of vehicles which are actually there. Using this data, what we do is we do a lot of analytics based upon this data that is there. A lot of effort goes into cleaning this kind of a data. So first is we have to identify whether a trip is a moving trip or it's a stationary kind of a trip, right? So whether it's the activity is it's a moving activity or a stationary activity. So that's the detection which we actually do, and we then calculate the energy consumption both for the moving activities and then the stationary activities by computing the instantaneous speed that is there for each of these different segments of this moving activity and then the stationary activity that is there, right? So a lot of the other steps involve, right, accurately calculating this emissions and fuel consumption both for the moving activities and stationary activities. And we use the state-of-the-art corporate model to kind of compute this energy consumption and then the emissions that are there. And the parameters that are there for this corporate model are estimated based upon the data that we actually have. Okay. So without really going into the details of this, I'll share the link to this paper, and you can kind of look at the details of this paper, right? So the key message from this paper, right, is that if you look at the red and the blue, so the red corresponds to 2017 and the blue corresponds to 2019, the first plot there shows, right, this the ones here, shows the speed, average speed that is there. The average speed you can see is decreasing, right, on an average this is for each borough in New York City, Queens, Bronx, Brooklyn, Manhattan, and so on. And you can see that the average speed decreases by on an average, about 22 to 25% in each of these different boroughs. Whereas if you see here, these are the emissions calculations. And the emissions are actually increasing in each of these boroughs, right, by about more than 50%, anywhere from 30 to 60% in each of these different boroughs, right? So you can see that, one, the speed decreases, two, the emissions increase, and the fuel consumption per kilometer has increased by about 18% in each of these different boroughs. So further analysis here shows the negative correlation with the number of FHV drivers and the average travel speed that is there. That means more the number of these Uber, Lyft drivers are there, more is the decrease in terms of the speed that you actually see in terms of these drivers. And we have kept pretty much everything the same across these 2 years, and there are no confounding effects that are there, right? So the key message from this is that the FHVs, right, be it Uber, Lyft, whatever it is, because of the increase in numbers that are there, result in inefficiencies leading to more energy consumption, resulting in more emissions, and you can quantify it using these types of tools and data, right? And what we have done is this for just New York City. So this, you can read all of the details in this paper, which is published here. Okay? And so the question now is, if we trust these numbers, now what can we do? So this is just for FHVs, but in a general setting, I mean, if you look at it in the context of more general electric vehicle-based ride sharing and so on, what can we do to kind of reduce the energy consumption that is there in cities, right, based upon the transportation movements that are there? For that, we need to first understand which are the highest energy consumers that are there in our transportation network, right? Not every facility, not every link of our transportation network is the same, okay? So there are some links which consume more, there are some facilities which consume more. So if we can prioritize that, right, and if we can have a better idea of which of these links consume more energy, we can better come up with solutions of reducing this energy consumption, right? So the key message here is, well, there is inefficiency, there is a scope for reducing this particular inefficiency due to the presence of FHVs that are there in this network. So now that leads us towards identifying the high energy consumption locations and links in the network, right? So the way we kind of look at that is, you know, I have one of my expertise is in network modeling for cities, right? So we develop various kinds of citywide network models. So the most simplest one is you can do all or nothing kind of an assignment, or the shortest path assignment of these various types of trips on the entire network, right? So this is a representation of this type of a network assignment. And then if you plot, right, based upon the current type of usage that is actually there, if you plot the energy consumption of these different links and by regions that are there in this particular network, you actually can see, this is the graphic which shows the energy consumption by trip origins. And what you see is that nodes or areas which have hubs. What is a hub? A hub is a point where a lot of trips start or end at any given point, right? So for example, in New York City, I mean, Madison Square Garden, which is like the key point where a lot of different types of transportation activity starts or ends because it has the Amtrak nearby, the transit stop nearby, a lot of employment opportunities nearby and so on. Penn Station, JFK, LaGuardia, and so on. These are all hubs, right? Because they attract and they generate a lot of trips that are there. And if you just focus your attention on these transportation hubs, what we see is that they actually contribute to about 26% of the citywide energy consumption in terms of the taxi and the ride-hailing services that are there, right? So instead of focusing our energy in terms of retrofitting the entire network, if we focus our attention first on these transportation hubs, right, and come up with operational ways in which we can reduce this energy consumption, I think that kind of helps us to attack the problem by making the energy consumption reductions in ones where they contribute to the highest, right? So for the nodes which are contributing to the highest, we focus our attention on that, and that will help us to then move to the other, sequence our attention to other types of nodes in the network. So with that insight, now what type of strategies can we come up with to reduce this type of energy consumption at hubs, right? And we have explored 3 types of strategies. One is first a routing strategy, which is related to reduction of energy optimal, which is a reduction of energy consumption using energy optimal paths. And so the second one is looking at a hub-based ride sharing by taking the most demand points and then kind of clubbing them together into high occupancy vehicles. And the third is flexible transit kind of service, right? So each of them will finally be integrated into the simulation platform that I'll quickly do a demo towards the end. So let's first look at the online energy efficient routing. So this is echo routing. And here we want to kind of assign the paths which reduce the most amount of energy to these vehicles, right? So if you look at the electric vehicles, and if you look at the key concerns which people actually have, in addition to the higher price point that vehicles have, one is the range anxiety, right? That people actually complain about, and this is one of the key barriers for adopting electric vehicles. So if we can increase the range by giving a more energy optimal path, even by let's say 10, 15, 20%, that kind of, in an urban setting, that kind of helps them to travel longer distances, right? So, but finding this energy efficient path in a network which is changing, right? The state of the network is changing all the time because of the environmental factors, right? So there's a lot of uncertainty in this network, and we lack granular data of the energy estimation to be able to give us very good path sets in each time period, right? So we formulate this problem as an online problem with stochastic estimates on each of these different links, right, with stochastic energy consumption. And we develop an efficient online algorithm to find these energy efficient paths. Essentially, we have to go from point A to point B, right? So there's a central controller who can observe the state of these links, but the state of the links are changing with respect to time, right? And how do we determine what path this vehicle has to take to the destination so that it consumes the least amount of energy, right? So this problem, right, so there's a lot of literature on online routing, including some of our earlier work in terms of where you can kind of incorporate some of the stochasticity. But the approach that we take here is related to a multi-amp bandit problem, right? So where there is a trade-off between exploration and exploitation, which means exploration, in the worst case, you can kind of enumerate the state of all of the paths that are there, and then you can kind of pick the best path. What's the challenge with that? If we were to do a full exploration of this,
There is no competition.
the computation, right? The computational cost is very, very high, and you cannot definitely do it in real time, right? Because the number of hyperpaths or the number of path possibilities are significantly large, right? The other idea is exploitation, which is basically you only focus on those actions which give you the highest reward, right? So you only look at a bunch of paths at any given time, and you pick the ones whichever give you the highest reward, and then you kind of go to the next iteration and so on, right? If you were to do this, just do exploitation, what's the problem?
Might be suboptimal.
It will be suboptimal because you might be missing some of the better paths that are there in the network because you may not be really coming up with the best reward in every case, right? So there is this trade-off between exploration and exploitation that we actually need to address. So we come up with some bounds for this combinatorial multi-amp bandit problem, right, by leveraging this information of the central coordinator. with some of the overlapping paths that are there. And if you look in transportation networks, one of the things that is there is there are a lot of overlapping paths. The path set might be very large, but there are a lot of overlapping paths, which means what's the problem there? The problem is there are a lot of correlations that you need to kind of address as part of your path set generation, right? So we develop a variation where you consider the variance and the correlations across these different paths that are there in terms of this energy consumption, and come up with the reward based upon accounting for both this variance and covariance of this path set. And then the final strategy which we choose is where we do path elimination, where there are overlaps, right, between these different path sets, so that we reduce those paths with very high energy consumption estimates, right? So we try different strategies of this MCUCB algorithm, which we have devised by accounting for the variance and covariance, and then by eliminating these path sets which are overlapping in nature. So some of the details of the math in terms of why this actually works and what's the difference between these different variants of this algorithm can be found in our recent paper, right? So I will just directly go to the results, and the experimental setting is this 10 OD pair matrix from Manhattan that we have taken, and we take different candidate paths are generated using some kind of a k-path, shortest path algorithm, and the base comparison that we do is with respect to a shortest travel time path and the shortest distance path that is there, right? So that's one of the benchmarks that we actually do, and then we compare across these different variants of this MCUCB algorithm, right? The plain vanilla one with and without this variance and covariance, and with and without this path overlapping matrix that is actually there. So if you run these algorithms, right? So these are some of the results that you actually have for this energy consumption with this different variants of these algorithms, and for different number of iterations for convergence of this algorithm, right? So again, here you have a centralized controller, right, and a decentralized action set that is actually taking place. So there is some amount of overhead involved in terms of this communication between the centralized coordinator and this decentralized action set that we actually have, right? So this can be effectively reduced by sharing this link level information among these different paths, right? And finally, the key takeaway is this MCUCB algorithm with the covariance matrix incorporated can reduce about 4% of the energy consumption, right? And as compared to the shortest distance path, and about 5.3% as compared to the shortest travel time path. Doesn't seem to be much, right? Doesn't seem to be a high number, about this 4% and about 5.5%. But when you add up across all of the vehicles and across all of the different path sets that you actually have, it reduces the energy consumption by about 1.2 kilowatt hours, and it extends the range by about 8 kilometers, right? And so it allows you to travel 8 kilometers additional distance for every EV that is there in the network. And that means you're able to take maybe 2 additional trips which you can do on any given day. In an urban setting, this is a pretty decent number for us. If you're doing long distance trips, doesn't make a big dent, right? But for an urban setting, I think this is a pretty decent number. And now when you add up this effect over all vehicles over a month or a year, the energy savings becomes significant for the entire network. So this is a first strategy in terms of using a energy efficient eco routing algorithm for reduction of this energy consumption. The second one is in terms of doing a hub-based ride sharing. Ride sharing, all of you are familiar with, right? So, but this is a slightly different variant where you focus primarily on the hubs, and from the hubs you have different amounts of demand. How do you put them into vehicles with different levels of occupancy, right? So some background I want to give you before jumping into that. So, I mean, we have been working on this for almost 9 to 10 years of work we have done in this FHV space and ride-sharing space. So this is one of our earlier papers here, and I think many of you might be interested if you're interested in ride-sharing. So this is one of the earliest works which have done, again, efficiency characterization of different types of ride-sharing strategies, right? And the key takeaway from that paper is as follows, right? That if you actually can meet all the trips that are there in New York City with only 2/3 of the TLC fleet that is actually there. That means you can almost reduce by 35% of the taxis if you were to efficiently do this matching between the ride and the driver, right? So because of our inefficiency, why is this inefficiency there? Because we are doing more of greedy type of a matching without really understanding the empty vehicles that are there when you drop off someone and pick up someone else, right? So because of that, we have about 1/3 of inefficiency that is there. The second insight based upon data, right, based upon analyzing millions of trips of data is from this paper. And what this tells us is this as follows, right? In New York City, and I mean, when I give New York City, I'm just giving it as an example, but because, I mean, New York City is, if something works in New York City, it works everywhere else, right? So, but you can, when I say in New York City, you can kind of substitute that with any city, really. So, based on the analytics of that New York City data, what we see is that if someone is willing to walk at most 3 blocks and wait at most 5 minutes, right? You can club about 80% of the trips into a ride sharing, right? So small changes like this in terms of how we make our trips can have significant savings in terms of the type of the occupancy of these vehicles and the type of ride sharing strategies that we actually can come up with, right? And if you increase those thresholds a little bit even more, you can actually club about 90% of the trips. And that's a very powerful insight, right? It shows that many of these trips can be, instead of having individual, of course there are other behavioral factors. One can say, well, not everyone is willing to kind of do a ride share. That's very fair, right? But many of these trips can be pulled together into a ride sharing service, right? So, and about 80% of them can be done with very little nudges that can happen, right? So these are two of our previous results from informed by a lot of data analytics and modeling and so on. So based upon those insights, we develop a novel ride-sharing algorithm that better matches passengers in transportation hubs. And the idea here is it's a look-ahead approach. That means you're not only doing it based upon what you see now, but you're making some prediction of what this demand is going to look like, right? Using a rolling horizon kind of a framework, okay? And based upon this prediction of this demand and supply conditions, right, we develop some kind of a stochastic optimization model, right, to link both these riders with the vehicles much better, and thereby reducing the energy consumption at these hubs, right? So this also accounts for the network structure, the hub-based network structure, to kind of efficiently generate the schedules related to these different vehicles. So 3 steps. 1, we have observations at time t0, right? And we make predictions for the future time interval, right, of different scenarios of supply and demand. Then we schedule the generation for each of these different scenarios, considering real-world constraints that are there in terms of how much, some of the behavioral things that I just mentioned before. Maybe somebody is not willing to, a male is not willing to drive with a female, or 2 friends want to be together, or I'm not going to take a ride-sharing service if it is sunny outside. So a lot of behavioral constraints can be put in that second step of the algorithm. And then the third part, right, is about efficient vehicle scheduling matching, considering the uncertainty that is there in this type of a problem, right? So without really going into the details, it's a Friday afternoon at 3:35, so I know our capacity to look at equations is pretty limited at this point. So this is a stochastic optimization formulation, right? And what we are trying to do here is we are maximizing the number of passengers who are actually served, okay? And this is what's called a recourse function, right? So, but we are trying to kind of make sure that the expected number of passengers who will not be served will be as minimal as possible, okay? And then on top of that, we have some of these realistic constraints, both on the demand side and on the supply side, we have some constraints. And now we need to kind of solve this type of a stochastic optimization problem with real world constraints that are there, right? So this is a pretty complex stochastic optimization problem. This is a large deterministic integer linear program. You can solve this using some kind of a stochastic approximation techniques based upon Monte Carlo sampling of this expected function. So one of the challenges is to kind of efficiently compute this expected value. So anyway, we come up with some efficient ways to solve this problem using Lagrangian multipliers and branch and bound techniques to actually solve that problem. Okay. Here is the key results that we actually have. Okay. The key results show that. So for that, when you account for the stochasticity, right? While you need to do more work, in terms of one, modeling it, understanding that uncertainty, and then solving potentially more computational time. You it saves more in terms of travel distances, right? So this is for different peak and off-peak hours. So this is AM peak, off-peak, PM peak, and so on, right? So you actually save by about 25% in terms of the distance traveled. You save in the off-peak by about 36%, and in the PM peak by almost 17%, and so on, right? So you get significant amount of distance savings, right, by using this type of a hub-based ride-sharing strategy, accounting for uncertainty in both the supply and demand side. But not only that, it doesn't end there. This also achieves better vehicle occupancy, right? Not only is the distance travel reduced, but also you can pack your vehicles more efficiently, of course, accounting for all the behavioral considerations, right? And that reduces the number of vehicles, the fleet size is also optimized by actually doing this type of a strategy, right? So the vehicle occupancy of different variants of this ride-sharing algorithm has also been tested with different thresholds of refresh times, right? So if we were to take the demand of every 30 seconds or 60 seconds or 120 seconds, make predictions at every 5-minute intervals or 3-minute intervals, right? So you can kind of test this strategy under these different conditions. And in all of those things, you can see that the vehicle occupancy is also kind of matched much more efficiently. Okay? So that's our second strategy in terms of that. The third one is more on a planning side of a thing. And this, I think, might be of interest to some people, including Samuel, with whom we have done some of this transit scheduling kind of application in an autonomous setting, right? So where we want to understand equity, community-related issues, and so on, right? So here, what we are doing is this is hub-based high-capacity mobility on-demand service for transportation hubs, particularly for like hubs like airports, railway stations, and so on, right? And this can be, of course, done for downtown centers, campus locations, and so on as well, right? And here you provide sufficient space for both passengers as well as luggage. You can also do luggage optimization or luggage scheduling using this. And it can be adjusted flexibly with demand on traffic, right? So this is not a fixed schedule like what we see for a bus, but this is a flexible schedule, right, based upon the real-time demand and real-time traffic that is actually there within this problem. So this has two challenges. One is a route generation. We have to determine the acceptable set of routes that this bus stops, where it will stop and what route it will take. And then the route optimization, we need to specify the number of buses for each of these different routes which we have selected, right? And this is a real service which is actually being tested in New York City. It's not fully operational, but it has been pilot tested on this bus line M60, which connects Manhattan and LaGuardia Airport in New York City. Okay. So we have three stages for this particular strategic solution. One, we want to generate a candidate transit routes from and to the hubs. We want to combine the different routes which are there in these hubs, and then we want to optimize the frequency, the fleet, and so on in this transit scheduling problem. Again, here we'll also consider uncertainty as part of this problem. So the problem becomes some kind of variant of a stochastic planning problem, where you have inputs related to the different demands of passengers and the different availabilities of this fleet. Okay? So you have route generation both from the hubs and the route combinations, which feeds into the fleet assignment, headway distribution, and route scheduling. Right? So I'll skip some of these in the interest of time. So we have algorithms related to route generation, route combination, and route optimization, which has all of the things related to waiting time of people, right, and waiting time of these buses, and then the operational costs that are there, right? So there's operational cost, passenger waiting times, and potential loss of demand, because you might lose some people if the bus is not coming there or not coming, waiting for enough amount of time. And then you can account for all the realistic constraints that need to be satisfied related to the supply and demand, about the trip time that might be there, and also account for the uncertainty which is there in terms of this demand, right? So this is a very interesting formulation. Of course, the challenge here is again scalability. How do you solve this efficiently, right? Because it becomes some kind of a min-max problem with a mixed integer programming kind of constraints that are there, right? So skipping all the details, okay, I'll jump directly into the results. And what we see here is we have generated, this is a small test that we have done before going into the large scale analysis for the entire network, right? So for this, we have generated the top 5 candidate routes with 60% of the demand, and 30 routes are needed to meet all of this demand, right? So this is the Manhattan, Brooklyn, Queens network, and we have generated about 30 routes here to meet all of this different demand. And as the number of routes increase, the number of passengers who can actually be served also becomes much better here. And what here you can see is that the upper bound and lower bound of this objective function actually converge as we are improving this particular optimization. And the optimization is pretty fast because of some of the heuristics that we actually use. It takes only about 300 seconds to actually solve this, with about 5 minutes. And the optimal cost increases as the uncertainty level increases. The more uncertainty you have, right, the cost of planning, right, the cost of planning involves what? The cost of planning involves basically the fixed cost of running this transit, and then the unmet demand, the cost associated with that, actually increases over a period of time, right? So these are our results for this smaller network. We also have results for the bigger network. I'm actually not showing here. But there's one important thing which you also need to think about, that there's also a trade-off that actually happens between the bus schedules versus if you are trying to schedule them in the taxis, and we'll see that in the simulation. Okay? So the final part which I want to share with you quickly is the simulation platform itself. This is a high-performance simulation. It needs to run in near real time on the size of a New York City kind of a network with all of these things which we just discussed. So it will integrate the operational tools, it will integrate the transit scheduling algorithms that we just talked about, right? And we want to test different scenarios. We want to test different energy policies. What happens if we were to electrify all the buses? We had no electrification of our taxis. What happens if we invest 50% on the buses, 50% on the taxis? What happens if we only electrify one corridor but not the other corridors? So what are the best corridors to electrify, right? So different types of energy scenarios we actually can test, and we can see the benefit not only from the energy consumption point of view, but also from the occupancy, the demand satisfaction, all of these other behavioral aspects of the problem. Do we have this kind of a tool right now? The short answer is no. We have a lot of micro simulations out there. We have a lot of macro simulations. But we don't have these type of AEV energy simulators which integrate these different kinds of operational tools and has a scalability in terms of running these type of planning and operational tools. So this is the architecture of this Metsar AEV simulation platform, right? So these are the inputs of the different things, including the road network, charging stations, parking, fleet size, right? Then the price if you have of the energy market, and so on. And then you have all of your different traffic simulation modules here. You have your operational models here, and then you have the visualization layer, and then the outputs from the simulator here. So these are some results from the simulator, and this is run on the hubs of JFK network, right? And this is a small case study which we have done to understand the challenges in terms of this data analysis. There are 5 levels of fleet, so that they are both AEV buses and AEV the taxis as well. And we have different fleet sizes that are there. So they are from 1,000, 2,000, until 6,000. And 3 levels of transit frequency have been tested. And there are different types of, you can see here, as the fleet size, taxi fleet size increases and the bus fleet size increases, the served demand increases, right? And that's obvious. And as your EV fleet size and bus fleet size increase, the waiting time decreases, and you can see by how much here. And as the passenger waiting time, you can also see it as a function of the EV fleet size and then the e-bus fleet size, and then the energy consumption. You can see here what's happening here. It's actually energy consumption is increasing as we increase, but after some point, it's actually decreasing per passenger mile. Why do you think that's actually happening? So this is, you're increasing the taxi fleet size, you're increasing the bus fleet size, and then the energy consumption is actually increasing per mile, and after some point, it's actually decreasing.
You're attracting more people.
You're attracting more people. That means here, the supply outpaces the demand here. That means you're adding more people, but you're adding buses and taxis at a higher rate as compared to the demand. But here, the demand is outpacing the supply that is actually there, right? So that's the induced demand that you actually have, which reduces the per mile energy consumption that is actually there. So you can also look at not only the net energy consumption, but also you can look at the energy consumption by different types. Like, for example, how much it takes for repositioning, how much is used for charging, how much is used when a passenger is occupied by a passenger, and so on, right? So you can kind of see the fractions of energy actually used by these different types of driving behaviors that might be there. We have done this on a larger network, right? So the larger network includes all of New York City, and it has a higher number of vehicles and a higher number of e-buses. And we have kind of evaluated this with every different strategy. So quick takeaway here is based on all the different scenarios. So these are the many different scenarios that we actually have run, where we have allowed bus scheduling. In some we have allowed bus scheduling, but no ride sharing and so on, right? So here you can see the different combinations of scenarios that we actually have run here. But let's focus on the key takeaway. The first key takeaway is there is no free lunch in any of these types of strategies. What do we mean by that? That means if the eco-routing can reduce the energy consumption, but it can potentially also decrease the number of passengers who are served, right? Because it may not really meet all of the requirements that are there in terms of the supply side. Similarly, the bus scheduling can increase the efficiency of the bus, right? But its interactions with taxi may actually worsen the energy performance, right? Just like we saw about the induced demand. So there is no free lunch. I mean, one strategy itself may not give us all the desired benefits that we actually would like to see. Okay. All right. So if we have time, we'll come back to this. So, I don't think we have internet here. Can we connect to internet? Gus, yes? Yeah. So this is a demo of our simulation. So all the things that I've just discussed today, we have put this into the simulation architecture, right? This simulation demo is available on our website here, but the source code is available also on our GitHub page. So if you go to my lab's GitHub page, you should be able to kind of find the source code of all of this. And we have worked with some software specialists to kind of create this output layer for the simulation, which shows different types of output metrics. And I will just show you some quick things that we actually can see here. So we actually can input the different number of vehicles of buses and taxis. And here you can kind of see how the vehicles are moving, the different trajectories that are there for these vehicles. And you can compute basically the energy consumption using a heat map that is actually there, right? So you can kind of see the energy consumption by different links. So if you want to zoom into any link, you can kind of see how this link energy consumption is changing. You can also look at the hub-based metrics related to how much of demand is actually being served. You can look at the energy per node, energy per link that is actually being consumed. And this is the heat map for 8:30 a.m. on a Saturday. You can kind of see the energy consumption, where it's consuming more energy, and so on, right? So you can kind of do this for different time periods. So you can kind of, students who are here, you can take a look at this simulation. You can kind of play around. You can also give some inputs to this. Okay, so I think we have like about 7 minutes, but I'll just take 2 minutes to talk about this. This is an ongoing work which we are doing. This is human-centered, data-driven charging stations. So this is, I think, a problem which many of the states and cities are working on right now in terms of what are the right places to build my charging infrastructure, right? And for that, I mean, right now I think everybody is in this Wild West phenomena where they're just going and building charging stations everywhere, right? But without really taking a data-driven approach to understand really where are the needs right now, where are the demand patterns, how can we use data to inform the EV charging trends, the travel trends that are there, and then make a more informed decision about building charging corridors rather than building just charging stations, right? So our work is planned with that direction to inform INDOT and the Indiana Economic Development Agency in terms of how they should strategically build not EV charging stations, but EV charging corridors in Indiana, looking at both short distance trip making behavior and also long distance trip making behavior, right? And the way we do that is, this is a work of some of my students, is using location data of travel patterns and using billions of trips right, over a long period of time, right, we look at the travel patterns. We look at how far people are traveling, where is the home location, depending upon their home location, how far are people traveling, what are the most different types of trips that we have observed during weekdays and weekends, how many long distance trips are there, and so on, right? So we use these different travel patterns to understand the EV charging patterns that could potentially be there under different scenarios of EV adoption for the future time periods. So we're primarily using, so there's a lot of analytics, I won't talk about all of that stuff, but we do home inference. We also have an algorithm which does EV vehicle detection, because all the mode is not given to us, so we need to detect whether it is a gasoline vehicle or an EV vehicle. So we have some heuristics incorporated in our algorithm to kind of detect these EVs, right? So these are the different charging stations. These are the gas stations. These are the different charging stations. And these are the different charging station visits which we have from our mobile phone kind of data, right? So we have for 1 month, this is 1 month of mobile phone data. We have about 7,230 trips which have visited charging stations, and about 300 out of the 323 charging stations have been visited at least once by these different vehicles that are actually there, right? And you can understand the charging behavior as to how many times they visit, if they visit a charging station, what are the other types of points of interest they actually visit, and so on and so on. So you can kind of see the OD demand within different urban areas, suburban areas, and rural areas. And these are some of the charging corridors that we have. This is a very preliminary result. We haven't even shared with INDOT yet, right? These are some of the charging corridors which we actually have been proposing, where a corridor is anything greater than about 100-mile distance, and 65, which is where Purdue is located somewhere here, right? So which connects all the way to Nashville, going through Chicago, right? So this is one important corridor, and you can see US 31, US 30, I-69. These are some important corridors on which we need to place these charging stations for the penetration to be much higher. Okay, I think I have a few more things, but I think this gives a summary of the type of things that we have done. Quick summary. So what you are seeing today is some of the results from our DOE project, where we are first motivated where the inefficiencies are in terms of energy consumption. We have come up with the hub-based as a solution, because hubs consume the most amount of energy, both from a demand and supply side. So we have come up with optimal ways in which we can develop operational algorithms for hub-based scheduling, and then transit scheduling using both operational tools and simulation methods. So some future directions, we are also interested in looking at dynamic pricing for this EV charging. We have some ongoing work on that. Human-centered infrastructure planning, understand how people are using these charging stations, not just in terms of the trip-making behavior, but is there a stickiness to the kind of charging stations that they will use, or do they keep changing every time? And then co-creating simulation tools, not just based upon the 2D simulation tools which I showed today, but using 3D simulators with realistic scenarios based upon Carla and Unity, these kind of simulation platforms. So this is some ongoing work which a couple of my students are actually doing. With that, I'll stop here, and thank you very much.
Thank you.
We'll go for questions.
I have a lot of questions. First of all, excellent presentation, very outstanding.
Thank you.
I'll try to be brief to allow others to ask questions. First thing is, it's interesting you were able to get hold of taxi data or Uber and all that stuff. Did they share it with you, or you have to buy it, or what was the method?
No, they did not share it with us. So if you go to the Open NYC, there are Uber trips, but they're only aggregate number of trips. What we need is trajectories for the analysis that we have done. So we actually collected this by ourselves using the API. And so we have basically, we found a bug in the API, and then we kind of collected the data through the API. And they've
But what is API exactly? What do you mean by
the API is basically the client interface for the app that you actually have. So you actually can talk to the client interface through the API. So we have collected this data by ourselves. So if you try to collect it now, you won't be able to do this because they have fixed that bug. So my students are always trying to kind of see, Samuel knows this, we are always trying to see where's the weak point through which we actually can collect the data when these data providers don't work with
the
us.
Uber app? That's what you.
That's right, Uber app, that's right.
And in terms of the emissions, did you use average speed to find the emission factor or real-time speeds,
Real-time.
acceleration, deceleration?
Real-time acceleration, instantaneous speed.
Yeah.
Instantaneous speed,
that's
instantaneous accelerations and
That's
acceleration.
more accurate.
That's right.
Now others to ask questions.
Thanks for your talk. I'm thinking about the part that you described about the demand adaptive transit scheduling. I think the optimization problem there that you described has several constraints, like say optimize people's wait time. That's like in terms of like minutes or something. And then there's the travel cost or transit scheduling cost. That's like the amount of dollars. My question is, how do you combine those factors?
So we normalize this, that's a good question. So we normalize the waiting time based upon the dollar values. So we have a VOT value for that particular city. So we use that to kind of normalize the time into dollars. And then we have the dollars for the scheduling cost and so on. So everything is kind of in terms of the dollar values.
Do you like assign different weights to those factors?
Yes, yes. So we have tried different weights for these different objectives that are there. I haven't shown all the results, but if you go to the paper, you'll be able to see the different scenarios that we have created. Yes, please.
So I'm very interested in the ride sharing problem. So I saw in the presentation your work did a lot of work on the hub-based ride sharing strategy or optimization method. So, but in our real world, I think not everybody will go to the hub for the ride sharing. So I want to know, do you think if we develop some optimization method or the ride sharing strategy for the people that will call the request for at any time or any place, do you think it will be more useful, or how we can do that?
Right. So first of all, this strategy is not for everyone, right?
Yeah.
Because not, as you said, not everybody is willing to go to a hub. Most people want a point-to-point service, right? But it doesn't have to be. So the hubs we discussed, at least in some of the experiments that I've shown, are very large hubs, right? Just focusing on that, you're able to get about energy efficiency of about 25 to 30%. Okay? But the point we are making here is that if we are able to have many more hubs, as I said, just by walking 3 blocks, waiting at most 5 minutes, you can create many more hubs, right? And even if 50% of the people participate in those hubs, you can reduce energy consumption by about 60 to 70%. And that's the hypothesis for this, all of this study, right? And so we fully realize that other 50% may not participate in this hub-based system, right? For various reasons. But if you're able to reduce the cost for those people who go to the hub and then participate in this type of a system, we can incentivize a lot more people to actually so this hub is not like you need to go a mile or even 2 miles or 10 miles, right? This is just like instead of on a nice day like this where the weather is nice outside, you just walk 3 blocks and you wait maybe additional 3-4 minutes and you're able to kind of do a pool ride with other people, right? And but that